Hi, this is Mrs. Nearing, and this is our ice charts video part 2. And an ice chart is a way to set up calculations involving equilibrium systems. This is something that's going to be useful in a lot of different applications, including KSP and acid-base scenarios. So it's important we get a good grasp on this technique now. And there are two types of problems we can use an ice chart to solve. Type 1 is solving for K when you're given some information about initial and equilibrium concentrations. And our first video on ice charts was about problem type 1. And this video is going to be about problem type 2, solving for concentration when you know the value of X. A quick review: the letters in ice stand for I represents initial, and this is the starting concentrations of reactants and products. A really key thing here is if the problem gives you a Kc value, all the values in your ice chart must be in molarity. And if a problem gives you a Kp value, all of the values in your ice chart must be in atmospheres. And you got to watch out for this because sometimes they might give you moles or volume, and you might need to use PV equals nRT to convert the values into atmospheres, or you might need to use that molarity is moles per liter, or they might just give you things in molarity or atmospheres. So just pay attention to the units that you're being given. Here's a sample problem, and you can see again I is our initial values, and notice that some of the initial concentrations might be 0. So like in this scenario, it says you've got a reaction where you're adding A and B to water, and C is not mentioned, so we're going to assume that there is no C to begin with. So some things might start at 0. C stands for change. The key thing about the change row is the values in this row should match the mole ratios from the balanced chemical equation. Remember, we find the mole ratios by looking at the coefficients. And we might know the value of the change, or we might use X to represent it if it's unknown. Other really important thing about change, the sign on the left side of the arrow will be opposite the sign on the right. So let's look at an example of that. You can see here that our mole ratio in this reaction is 2 to 1 to 3. You can see that from my coefficients. So in my change column, it's going to be 2x, 1x, and 3x. So change row needs to match your mole ratios, your coefficients. And notice on the left, the reactants are being used up, so it's a negative change, and on the right we are making products, so it is a positive change. So sign is opposite on opposite sides of the arrow. Equilibrium represents your final equilibrium point, and you find it by adding the values from initial and change. Alright, so now let's apply this to a problem in which we're given a K value and we're trying to solve for concentration. So here's this practice problem. We've got COCl2 allowed to come to equilibrium, and we've got our balanced chemical equation right here. They give us a value of K, and we tell us a molarity and a liters. So we know that since this is a Kc expression, all the values we use need to be in molarity. So we're going to use molarity equals moles per liter to turn these values right here into something we can use. Okay, so let's flip over to the next page and get an ice chart set up here. So I'm going to write my Kc expression first. So it's Kc, so I'm going to use brackets to represent molarity. If it were Kp, I would use the symbol P for pressure. So there's my Kc expression, and then we're going to plug in here what we know. So we know the initial moles in volume of my reactant. Okay, so this is 0.194 moles. But I can't just leave this in moles. I have to convert it to molarity. So I'm going to divide it by my volume, 5.8 liters. And that gives me 0.033 molar. And the products are not mentioned, so we're going to assume that those start at 0. So we're starting out with pure reactant. And that is all we know in terms of concentration. So for my change column, I'm going to use the symbol X to represent change. So I'm starting with reactants, and some of my reactants are going to get used up, and then we are going to make some product. And notice it's a 1 to 1 to 1 mole ratio. So these are just all going to be X, X, X in my change row. And the left is negative because it's being used up. The right is positive because my products are being formed. And then equilibrium is 0.033 minus x, and then this is x, and this is x. So now I'm going to go down here and plug values into this equation I just wrote. So 7.27 times 10 to the negative 38, because they gave us this k value, and CO is x, Cl2 is x, and then this is 0.033 minus x. This ends up being x squared divided by 0.033 minus x equals 7.27 times 10 to the negative 38. So we have an equation with one unknown. So yay, we can solve for x. The only problem is, look at this equation. How do you solve for x here? You'd have to use the quadratic formula to solve for x. So that would be a pain. Luckily, there is this approximation that we can use in most cases. You got to double check to make sure that it fits. But the rule is, if the difference between k and the initial concentration is about 3 orders of magnitude, then that means x, the value x, is going to be much smaller than the original concentration. And since x is so much smaller, since the change is so much smaller than your initial concentration, the initial concentration is basically going to remain unchanged. So, like, here's an example here. If you take 2 molar minus 0.00000001 molar, your answer is 1.99999, which is basically just still 2. So what we do here is we say, okay, 2 minus x. If x is really small, we can just ignore x and say 2 minus x is just 2. So this only works if k is sufficiently small. So let's look back at this problem here. So notice how k is 10 to the negative 38. That is tiny. Okay, so k is very small, meaning x is very small. So let's write down this assumption that we're going to make. So since k is so much smaller than my initial molarity, then we will assume that 0.033 minus x is just equal to 0.033. Okay, so that is going to make our lives a lot easier here in this calculation, because now we can simplify it and say, okay, it's 7.27 times 10 to the negative 38 equals x squared, and on the bottom, instead of writing 0.033 minus x, we're just going to write 0.033. Okay, and that's a lot easier to solve for. So you end up with x equals the square root of 7.27 times 10 to the negative 38 times 0.033, and you go through, you plug that in your calculator, x equals 4.9 times 10 to the negative 20th. And if you're wondering what the unit should be here, remember our rule that since this is a Kc expression, all the values in this table are in molarity. So even though K is unitless, we are assuming anything from this ice chart is going to be in molarity. So the units of this are molarity. Okay, so summarizing our, I'm going to flip to this slide, which kind of summarizes the answer. And it's important that you go back and make sure you answer the initial question. So we solve for x, but the question asks us what are the concentrations of all my species, so reactants and products, at equilibrium. So you want to make sure you go back and answer that question. So CO and Cl2 are both 4.9 times 10 to the negative 20th, and then COCl2 is 0.033. And it's good to check your assumption. You know, we made this assumption that 0.033 minus x is basically just 0.033. And we can check that assumption by try plugging this in your calculator. 0.033 minus 4.9 times 10 to the negative 20th is going to be 0.032999999. So it is still 0.033. So that was a good assumption. That's always good to go back and check. All right, here's another practice problem so let's take a look at this. So we've got nitrogen gas and oxygen gas reacting to form nitrogen monoxide. Chemist mixes 80% nitrogen and 20% oxygen by moles in a vacuum and finds that the total pressure is 1 atmosphere at 25 degrees Celsius. And we are given a K value for this reaction. And I realize I didn't put the rest of the question here. So we want to find, so the question would be, find the pressures of these species at equilibrium. Okay, So what I'm going to do is I'm going to set up an ice chart. So I'm going to rewrite my reaction down here. There we go, 2NO. I'm going to do ICE. And notice how they give us a Kp value. So when we're setting up our ice chart here, since it's a Kp, all of our values need to be in atmospheres. And then let's write out our Kp expression. Kp equals the pressure of the product. So we'd use the symbol P, and that's going to be squared, because there's a coefficient 2 there, divided by the pressure of oxygen and pressure of nitrogen, my reactants. All right, so we need to plug in atmospheres, but they give us this thing with percentages here. So what we actually want to do is go back to our knowledge of gas laws. And do you remember we had this equation, the pressure of A equals the mole fraction of A times the total pressure? So what that means is like the pressure of N2 is going to equal the mole fraction of N2, which is what this problem is telling us. It's 80% N2, so it's 0.8. And the total pressure is 1 atmosphere. So what that means is the pressure of N2 is 0.8 atmospheres. Okay, so 0.80 atmospheres. And we do the same thing for O2. It's 20% O2, so 20% of 1 is 0.20 atmospheres. And initially, we're just putting in a reactant. There's no product to begin with. We don't know anything about their values at equilibrium, so we're just going to use X to represent our change. So our reactants are going to get used up, so they're going to be minus X. Our products are going to be made, so it's going to be a positive change. And since it's a 1 to 1 to 2 ratio, I'm going to use 2X to represent my change in products. So equilibrium here is 0.8 minus X, 0.2 minus X, and this is just 2X. So now I'm going to go and plug these values into my K expression. So I know the value of Kp is 1 times 10 to the negative 30th. NO, my pressure of NO, I'm using 2X to represent that. And then don't forget to square it. And then on the bottom, I've got 0.2 minus X, and I've got 0.8 minus X. And this is, I've got one variable, so one unknown and one equation, so I could solve for it, but this would be a big pain to solve. I'd have to do FOIL, I'd have to use my quadratic formula, this would be a big pain. But remember, hey, check this out, our K value is really small, so K is 10 to the negative 30th. It is much smaller than our initial pressures, so that means we can use our simplification and we can say 0.2 minus X is just 0.2, because that change in X is so small compared to the 0.2. 0.8 minus X is just 0.8. So I'm making that simplification. On the top, it's 2x squared, so don't forget to square the 2 and the x. Okay, so it looks like that. And then we're going to go through and we are going to solve for x. And I ran out of room, so I'm going to flip to the next slide here. So here's our setup. When you go through and you solve for x, you end up with x equals 2 times 10 to the negative 16. And then don't forget to go back and answer the question that is being asked, because the question didn't say solve for x. The question said, what are the pressures of everything at equilibrium? And if you look back to your ice chart, we define the pressure of nitrogen monoxide as 2x at equilibrium. So if x is equal to 2 times 10 to the negative 16th, that means the pressure of my product is actually 4 times 10 to the negative 16th. And then the pressure of my reactants remains unchanged because we subtracted such a tiny number from that. Like 0.8 minus 2 times 10 to the negative 16th is just still 0.8 because that is such a small number. All right, so these are two practice problems with examples of how to solve for concentration or pressure when you know the value of K. And let me know if you have any questions.